Hello students. So last video I promised you that we were going to get around to showing that the null space is a subspace. And we are. Just I want to do one more example. Well, maybe more than one. I know, we're putting it off. We're not delaying. These are nice examples to think about. So just let's say we have some t from v to w. I'm not telling you what v and w are, but let's say I define the map to be tv equals 0. It's a nice simple example. So I'm saying, hey, t is the linear transformation that sends everything to 0, no matter what that thing is. Okay, well, is this linear? Stop and think about it. Yes, it absolutely is linear. Why? Well, because t of v plus w is going to be 0. But t of v plus t of w, that's 0 plus 0. And similarly, for constants, for scalar multiples, if I have t of lambda v, well, that's going to send lambda v to 0. But lambda times t of v, since t of v is 0, I'm going to get 0 again. So lots and lots of 0. All the way around, I get zeros. So what do I have here? I have a linear transformation. What is the null space? Well, the null space is a set of things that go to 0. What goes to 0? Everything goes to 0. So I get the null space of t equals all of v. All of v gets sent to 0. So that's another nice little example. Another example I could give you guys is, hey, let's let t, which goes to v, from v to v, be the identity map. We've talked about identity maps as well. So the identity on v. So what here would be the null space? Well, one more time. We'd want the set of vectors so that t of v equals 0. But t of v is equal to v. So I want the set of all vectors that go to 0. But t sends vectors to themselves. So I want the set of all v so that v is equal to 0. So what do I have here? I just have the 0 vector in v. Here, this 0 is the 0 vector in v. So v could be abstract, any weird vector space you could think of in this example. V and w could be any weird vector spaces you could think of in those examples. These are for any vector space, all inclusive, not specific to any vector space you could think of. Whatever weirdness you could imagine, you can always take this transformation and that transformation, and these will always be the answers. This will always be the null space of t, and this will always be the null space of t in that example. Okay, but let's get around to the next part, which is what I've promised. I said I was going to show you that the null space is always a linear transformation, always a subspace. We don't have a null space without a linear transformation. Okay, so let's do that. So let's prove the null space of t is a subspace of v. I mean, obviously it's a subspace of v and not a subspace of w, because we're looking at all the v's that which can be put into t. We're not looking at the outputs. We're looking at all the v's that can be put into t that send ourselves to 0. So the set of all v's so that t sends that little v to 0. That's what the null space of t is. So let's do this now. What am I going to get? Well, I want to show that this is a subspace. Okay, so let's even write proof. We'll do this super rigorously. Okay, so what do I want to show? I want to show, suppose R and S are in the null space of t. I decided on R and S for my elements this time. So what do I want to show? I want to show that R plus S is in the null space of t. But what do I know? Well, if R is in the null space of t, we know t of R is 0. And we also know that t of S is 0. So what do I find out? Well, t of R plus S is equal to. Why is this equal to it? Because t is linear. So here we're using the linearity of t, just the linearity of t. And here we're using the fact that T of r is 0 and T of s is 0. And here we're adding 0 in W, but 0 plus 0 is 0 no matter what vector space I'm in. So I get 0. So what does that mean? It means r plus s is in the null space of T, because T sends r plus s to 0. Now we have to show scalars. That is, if I have something in the null space, lambda times that vector is also in the null space. So let's do that. Now let's suppose lambda is in the field and r is in the null space. So what do I know? Well, I know that T of lambda r, well, T is linear, so I'm using the linearity of T. Now I'm using the fact that r is in the null space, which means T of r is 0. Now I'm using the fact, which we proved a long time ago, it's not an axiom, but that lambda times 0 is going to be 0 for any scalar lambda. And oh, look, what did I show? I showed that lambda r gets sent to 0, so lambda times r is in the null space of T. So what have I done? I have proven that, oh, let's do a little, yay, I'm done, I can celebrate, mark. So I've shown now that the null space is a subspace. It is closed under addition and scalar multiplication. That means if you take two things in the null space and you add them, you're in the null space. If you take a scalar times something in the null space, you're still in the null space. So null space is going to be very important for all sorts of things in linear algebra. Not just the fact that we're often setting things to 0 when we're solving them, but for a number of reasons, which we can't go into all of them right now. But it's behind some of the most important theorems in linear algebra involved in null space as one of the components. We're going to talk a little more, but let's save that for the next video.